In this video, I will review the quiz questions about solutions. First question, which of the following are considered a solution? A solution is a homogeneous mixture that is uniform in composition throughout. So this is very important. Rubbing alcohol, yes, we have the same concentrations of water and alcohol everywhere. Same in this metallic alloy. Metallic alloys are always a solution of metals. A mixture of gases is always a solution. This is table salt completely dissolved, so it's a solution. Mixture of sand and magnesium, this is not a solution because you can easily find just a grain of sand with 100% of sand and 0% magnesium. And then you can find, just a bit magnesium powder that contains 100% magnesium but 0% sand. Club soda, carbonated water. So it's yes, unless you clearly see bubbles or in this water, big bubbles, and then it's not really homogeneous. Hexane is insoluble in water mainly because to dissolve hexane in water, you have to break the hydrogen bonds between water molecules. And you have to break the attraction between hexane molecules via dispersion. It's called dispersion or London force. It's true that there is indeed some attraction between hexane and water, but that attraction is very small compared to the hydrogen bonds or the dispersion between hexane. Entropy is a measure of the randomness. When water and ethanol are mixed, the entropy increases. When pure A and pure B are mixed, to mix A and B, you have to break the BB attraction and AA attraction. And also, there's going to be AB attraction being formed. So we'll select this 3. The magnitude, this 3. The entropy of the system increases after you mix two pure chemicals. So this is wrong. The enthalpy of hydration is the enthalpy change of the following process. So we'll have to select one of the 3. So which one is the particles solvated by water? That means hydration. So this one. Over here, table salt is dissolved in water. Yes, in this process, solvated sodium plus and chlorine minus are also formed. But the starting point is table salt. So it's not really the hydration of table salt. All right, so the question is about the enthalpy of hydration of separated sodium plus and chlorine minus ions. Oh, and by the way, this process, when table salt is dissolved in water, it's called dissolution, or enthalpy of dissolution, or enthalpy of solution. So enthalpy of solution, also known as enthalpy of dissolution, is to dissolve table salt. The difference between the enthalpy of solution and the lattice enthalpy of sodium chloride is, so look at here and here, both involve the table salt in the solid phase. However, when you are talking about enthalpy of solution, we're talking about table salt becomes solvated sodium plus and chlorine minus. In the lattice of enthalpy, we're talking about sodium plus and chlorine minus in the gas phase. So really the difference is the enthalpy of hydration of sodium plus and chlorine minus. All right, 8 out of 8. At 25 degrees, the solubility of potassium chloride is 34 grams. What if 32 grams is fully dissolved? Okay, it's unsaturated because we can dissolve more. What if we dissolve exactly 34 grams? Well, it's saturated. All right, now what if we add 35 grams of KCl into 100 grams of water? So still only 34 grams can be dissolved. There's going to be 1 gram of KCl in the solid phase. At 25 degrees Celsius, the solubility of KCl is 34 grams in 100 grams of water. Okay, how can we dissolve 35 grams at this 25 degrees Celsius? It's possible. We can dissolve more KCl at a higher temperature. So we'll just do that. We dissolve 35 grams of KCl at a higher temperature. And you carefully lower the temperature back to 25 degrees Celsius. As long as you do not disturb the solution, you do not introduce, for example, the seed crystal, just tiny bit of KCl crystal in the solution, this so-called supersaturated solution is metastable. So really it's unstable, but yet it does not precipitate out the KCl yet, unless, for example, you scratch the inside of the container, or you add a little bit KCl crystal, the so-called seed crystal, to start the crystallization. So we're going to choose this one. Question 5, based on like dissolves like rule, which two of the following pairs are miscible? Vegetable oil and coconut oil have similar structures. Water and methanol have similar structures, and these two are both polar. Water and oil, no. Sodium chloride, that's ionic. Vegetable oil, that's more like nonpolar. It's a little bit polar. Liquid A can definitely be dissolved in liquid B if the dissolution is exothermic. If dissolving A in B releases heat, this is going to happen. Liquid A can often be dissolved in liquid B at a higher temperature, even if the dissolution is endothermic. So high enough temperature. You can try this at home. When you wash dishes, if there's some oil on the dish, if you use hot water, it's easier to dissolve the oil than using the cold water. Silver chloride does not dissolve in water, so there are two reasons. First, the energetic reason, and two, we're going to talk about entropy. So first, if dissolving a chemical in water releases heat, that chemical is soluble in water for sure. So one thing we know, it's going to be endothermic. All right, so we click endothermic. Not only that, we have to understand that in this dissolution, silver chloride does not dissolve in water only because the entropic effect, this T delta S, is less than delta H. So delta H is greater than T delta S. Right, so there's two reasons. So not only this delta H is positive, endothermic, that means delta H of dissolution is endothermic. It's not only greater than 0, but also greater than temperature times the change of entropy in the dissolution process. Question 9. When we mix two gases, okay, obviously the entropy increases. So we say the entropy of mixing is positive. The entropy of mixing is the change of the entropy in the mixing process. And 2, because these two are noble gas atoms, so I'm going to say the enthalpy of mixing is roughly 0. Question 10. When 1 mole KOH is dissolved in 9 moles of water, let's say the volume is roughly 110 milliliters. Let's calculate the mole fraction and mole percentage. Well, that's very simple. The total number of moles 1 plus 9, that's 10 moles. And then we use 1 mole over 10 moles, that's 0.1 and 10%. Now mass percent. This time we'll have to compute the mass of KOH and the mass of water. You look up the molar mass of KOH. I think K is 39, oxygen is 16, H is 1. Together we have 56 grams of KOH. Water has a molar mass of 18. 18 times 9, that's 162. So what's the total mass? 56 plus 162. So I think it's 218, and you just need to do a division. 56 grams of KOH divided by the total mass, which is 218, and we'll get 26%. Well, 1 mole KOH is dissolved in 9 moles of water. The volume is given to you. What's the molarity? So the definition of molarity is the moles of the solute divided by the volume of the solution. So 1 divided by 0.11 liters. Okay, so it's going to be 9.1 molar. When 1 mole KOH is dissolved in 9 mole water, this time we're going to calculate the molarity. Molarity is the number of moles of the solute divided by the mass of the solvent in kilogram. So if we look at the molar mass of water, it's 18. 18 times 9, it's 162. We're talking about 0.162 kilograms. So it's going to be 1 over 0.162. So it's going to be 6.2 molo, and we submit the quiz. 8 out of 8. This is a review question on chapter 11. So chapter 11 is about liquids and solids. So the thing is, the water vapor pressure of pure water is 355 torrs at 80 degrees. And if the external pressure is only 350, then water vapor pressure is higher than the external pressure. It's possible for this liquid water to form bubbles of water vapor, and because the pressure of this bubble, water vapor bubble, is 355 torr, higher than the external pressure, the bubble is going to float to the surface of the liquid and burst. Therefore, boiling is possible. Now, water vapor pressure is 355, and then this time we're going to add a little bit glucose in water. So how much glucose? Only 0.2 moles into 9.8 moles of water. So what's the mole fraction of water? 0.98. So it's 9.8 divided by 10. So 0.98. What's the water vapor pressure? 0.98 times 355. All right, so that's 348. Slightly lower than the water vapor pressure of pure water. All right, now again, can this solution boil? Well, this time the pressure is 348, lower than 350. So the external pressure is higher than the water vapor pressure. And this external pressure will suppress the formation of the water vapor bubble. So no, it's not going to boil. The vapor pressure of water and ethanol are this much, 0.03 and 0.08. And then if we have a mixture of 9 moles of ethanol, 1 mole of water, what's the total vapor pressure? So really we need to just sum up the vapor pressure of water and the vapor pressure of ethanol. First, let's look at the mole fraction. It's very easy. Ethanol 0.9, water 0.1. So 0.9 times 0.08 plus 0.1 times 0.03, that's this one. And also there's another way to look at this more qualitatively or semi-quantitatively. You look at this, it's mostly ethanol. Therefore, the vapor pressure of the mixture should be close to the vapor pressure of ethanol, and then you can just select this answer. The vapor pressure of water and ethanol are 0.03 and 0.08 atm, and then this time I give you the total vapor pressure. It's 0.06. So let's calculate the mole fraction of ethanol. So let's say the mole fraction of ethanol is X, and then the vapor pressure of ethanol is 0.08x. Alright, that's the product of this 0.08 and the mole fraction of ethanol, X. What about the water vapor pressure? It's 0.03 times the mole fraction of water, which is 1 minus 0.03x. So really it's just 0.03 times 1 minus x, and then plus 0.08 times x equals 0.06. You set up the equation, you solve the equation, I think you'll get 60%. Another way to look at this is 0.06. Again, is closer to ethanol number. Therefore, it's likely or very likely that we have a solution that contains more ethanol than water, so 60%. Now the vapor pressure of water and ethanol are 0.03 and 0.08 atm. The total vapor pressure is given to you. What's the mass percent of ethanol? All right, we know the mole percent, it's 60%. But we need to know what's the mass percent. So you need to convert this number of moles of ethanol to the number of grams. So over here, let's make it a bit easy. Let's say we have 0.6 moles of ethanol and 0.4 moles of water. So that's a solution that contains 60% of ethanol. Again, 0.6 moles of ethanol, 0.4 moles of water. And then we need to convert this to numbers of moles to the numbers of grams. So 0.4 times 18 gram per mole, that's for water, you get 7.2 grams of water. What's the molar mass of ethanol? The formula is CH3CH2OH, so you have 2 carbons, 6 hydrogens, and 1 oxygen. Therefore, the molar mass is 24 plus 6 plus 16. The result is 46 gram per mole. The molar mass of ethanol is 46, and then times 0.6 mole. Okay, we're assuming 1 mole solution, therefore 0.6 moles ethanol plus 0.4 moles water. So that's our assumption. And 0.6 times 46, that's 27.6 grams. So we have 27.6 grams of ethanol. We have 7.2 grams of water. What's the mass percentage of ethanol? It's 79%. Again, 27.6 divided by the sum of 27.6 and 7.2. So if you do the calculation, it's going to be 79%. Okay, why don't I just show you how to use Google to compute this. Again, let's assume we have 1 mole solution. So inside this 1 mole solution, there's 0.6 moles of ethanol. That's the mass of ethanol, 0.6 times 46. Let's say we have 0.4 moles of water times the molar mass of water. We're going to get a number. It's 0.79, therefore 79%. All right, so this is a mass of ethanol, mass of ethanol, mass of ethanol, mass of water. All right, so that's that. Let's get back to question 7. If the vapor pressure of benzene and toluene are 75 and 22 millimeter mercury, what's the total vapor pressure that contains 10 mole benzene and 10 mole toluene? So the numbers of moles are the same. So we have 0.5 mole percent I'm sorry, 50%, 50 mole percent of each. So really it's just 75 times 50%. And then you have 22 times 50%, and then you sum it up. The result is going to be 48.5. All right. Oh, by the way, 1 torr is 1 millimeter mercury. 4 out of 4. The boiling point of a salt solution, this is table salt solution, is approximately how many degrees? This is a little tricky, because when we dissolve sodium chloride in water, it dissociates into 2 particles, sodium plus and chlorine minus. So when we do that, the actual molarity of particles is twice the molarity of sodium chloride. If you do 8 over 2, you get 4 molo. That's the molarity of sodium chloride. But really, the molarity of the particles is 8. So what we need to do is we need to use this 8 times this the constant for boiling point elevation. I think it's 0.512. So 8 times 0.5, that's 4 degrees. And it's boiling point elevation. So the result is 104 degrees Celsius. The melting point, same thing, but the melting point depression has a different constant, 1.8 something. So what we need to do is, again, we'll look at this molarity of sodium chloride, that's 4 molo. But then if we're looking at the particles, it's 8 molo, so 8 times 1.8 something, that's 15. And also, this is so-called melting point depression. The melting point decreases to negative 15 degrees Celsius. Now, osmotic pressure of the same solution. Well, this time, same thing. What you need to do is you need to look at the number of particles. That's going to be 16 moles instead of the number of moles of sodium chloride, because sodium chloride dissociates completely into sodium plus and chlorine minus. So really you have 16 moles of particles in this 2 liters of water. The molarity is 16 over to 8 molar. So if you use 8 molar times R times T, it's going to be 8 times R. R is 8.3, and then times T. T is, let's say, 300 Kelvin. And don't forget to multiply your number by 1,000, because molar is not an SI unit. If you're talking about 8 molar, it's 8 moles per liter. Therefore, it's equivalent to 8,000 moles per cubic meter. So really, if we stick to SI units, you should do 8,000 moles per cubic meter times 8.31446 joule per mole K. That's R, the ideal gas constant, times the temperature. Let's assume it's 300 Kelvin. And then the result is going to be 200 bars. So this is very surprising. The osmotic pressure of a saline solution. This time we use 4 moles of glucose and 4 moles of lactose. Compared to this question, we also have 8 moles of solute. But in this question, this solute, neither solute dissolves, dissociates in water. So we're talking about just a total of 8 moles of solute dissolved in 2 liters of water. So it's just 4 molar. The concentration is only 50% of that in question 3. So when we're talking about this osmotic pressure is equal to CRT, the concentration, or moles per unit volume times R times T. And then if we have only 50% of the concentration, we have 50% of the osmotic pressure. So compare this 200, I'm going to select this 100, which is 50%. The Van der Hoef factor of magnesium chloride is 3, because this decomposes into 1 magnesium 2 plus and 2 chlorine minus. It generates 3 ions, so that's number 3 here. The osmotic pressure of a saline solution, again, a saline solution I'm sorry, I should delete this saline solution. Saline solution is a aqueous solution of sodium chloride, so I probably should delete this word. I need to change this to magnesium chloride solution. In this case, we have actually 24 moles of particles in 2 liters of water. So the molarity is 24 over 2, that's 12 molar. 12 molar is 1.5 times 8 molar, so it's going to be 1.5. The osmotic pressure is going to be 1.5 times 200. So without doing too much calculation, I compared the concentration of particles in this question, which is 12 molar, with this one, which is 8 molar. This one, which is 8 molar. So 12 molar is 150% times 8. Therefore, 200 times 150% is 300. So that's how I got this number. Again, this is because the osmotic pressure is equal to CRT. And R is a constant. And if we assume there's no temperature change, just the room temperature, and we can just assume the osmotic pressure is proportional to the concentration. Therefore, if we increase the concentration by 50%, we increase the osmotic pressure by 50%. Question 7. Colligative properties do not depend on the type or nature of the particles or size of the particle. Colligative properties depend only on the numbers of the particles. Six out of 6.